General procedure for sketching the graph of f of x. Find the domain, that's algebra. Plot all intercepts, x-intercept, y-intercept, and it says you may require a calculator, and that means that if it's a quadratic equation, and that's easy peasy, that's quadratic formula, but you could use a calculator. However, if it's a QB, fourth degree polynomial, some other oddball function, you may need to use your calculator. I can show you how to do that, or do a little video that you can review that if you wanted to. Use your graphers, certainly as a way of doing it. Determine all horizontal and vertical asymptotes in the coordinate plane. Now notice the first three steps are algebra. That's algebra. Step 4, find f prime, use it to determine the critical numbers and intervals of increasing and decreasing, determine all relative maximum and minimum, etc. So step 4 and 5 is f prime. Step 6, now find f double prime, use it to determine the intervals of concavity and points of inflection, plot them all with a twist, blat, 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 blat. F double prime. Now you have a preliminary graph with asymptotes in place, intercepts plotted, arrows indicating the direction of the graph, caps, that's maximum, minimums, twists, etc., etc., etc. And so you can now do the graph. And by the way, you may need extra points. And one of the problems we're going to do, you will. I find that kind of messy. So what I developed in the engineering calculus class, and then what we did is, embellished it and brought it down, is this. Translating it into a template for graphing each problem. Layer 1, algebra. Domain, vertical asymptotes, end behavior asymptotes, x and y intercepts. 2, first derivative, increasing, decreasing, maximum, minimum. 3, second derivative, concave up, concave down, inflection points. 4, graph, put all the above information on the graph, plot any additional points if needed. That's all that is saying in a very concise form. Now from that, and this is available, by the way, on Canvas as something separate. If you want to do your homework on these, you can. I developed a template. Now the template, normally what it's got, it just has f of x. You put in the function that you're working with. And then you just follow it down through. Page 1 is algebra. Page 2, all it's got is f prime and f double prime. It's calculus. Now I won't be actually doing the derivatives. I assume that you can, or if given enough time that you can. We're going to be working with the derivatives as they exist. That'll be true for this kind of problem on the exam as well. I'll be giving you the function and the first and second derivative, and you'll be doing everything that you need to do with that. Okay, so here we go. X plus 3 over x minus 5. Looking at f of x, we start off the algebra. Find the domain. Well, the domain, remember the denominator can't be 0, so x minus 5 can't be 0, or x can't be 5. Now that means I'm dealing with all real numbers except for 5. Now this is kind of an easy domain. One of the reasons why we do domain is, remember that in the case where we had one number line that went from minus infinity to 9, you need to know when you're going to start pulling points and putting critical numbers what's your domain so you can eliminate those things that aren't in it. I notice I do have a piece of graph paper, so there's my graph paper. Intercepts, x-intercepts. Now x-intercepts is where f of x equals 0. That's where the numerator equals 0. Because remember, where the numerator equals 0 is essentially where you're going to have x-intercepts where the denominator equals 0, or critical numbers. Where the denominator equals 0 is where you've got VAs, or potential VAs. So that's where the numerator equals 0, or x plus 3 equals 0, or x equals negative 3. So I do have an x-intercept at negative 3, 0. Only one, that's nice to know. Y-intercept is where x equals 0. So that's where I take the original function. So it's 0 plus 3 over 0 minus 5, which is 3 over minus 5, or it's 0, negative 3/5. So I do have a y-intercept, and I have an x-intercept. The next thing I go after are the vertical asymptotes. That's where I have a pure division by 0. I should put in the word in here, pure, because we know 0 over 0 is a hole in the graph. It's not going to be a VA. But we do have one, and that comes from where the denominator equals 0, and of course that's x equal 5. And horizontal asymptote is the limit as x goes to either plus or minus infinity of, and let's find out what the model is. The model is what? X over x, which is 1. So that's the limit as x goes to either plus or minus infinity of 1, which is 1. So that says I have an HA at y equal 1. Now I change pen colors, and I go up, and by the way, in college algebra, this is really enough information to do the graph. And I go up to my graph paper, and I put the information I have. I have an x-intercept at negative 3, 0. I have a y-intercept as 0, and it's slightly less than 1. I have a VA at 5, 1, 2, 3, 4, 5. And I have an HA at y equal 1. Now, if I am in college algebra, what we tend to do is say, well, this is going to run along the HA. He's going to continue, because he's moving downward, down along the VA. The VA is multiplicity 1, so that means if it's going down on one side, it's going up on the other. And then it comes down and rides along the VA. So that's what we do in college algebra. But this is not college algebra. This is calculus. But that's what we're going to expect.